6, whenever we deal with a source of current, that source was cell or battery, your current was DC. DC means this current does not change with time. Its magnitude as well as its direction remains constant with time. This type of current is known as DC current. After DC current, you have one more type of current which is known as AC current. Alternating. Alternating means both the magnitude as well as the direction of current will change periodically. AC is like this. Both magnitude of current as well as the direction of current is changing periodically. Both magnitude and direction are changing periodically. This type of current is known as AC current. It does not remain constant. It changes continuously with time. This type of current is AC. The source of AC current, source of AC is dynamo or generator. This is the source of AC current, which is dynamo or generator is a source of AC current. So we have already studied cell. Now we will study that how will you build AC generator and on what principle this AC generator is based. Okay, let's start with AC generator or dynamo. AC generator or dynamo. So this AC dynamo or AC generator is based on Faraday's law of electromagnetic induction. It says whenever magnetic flux linked with a coil change, EMF is induced in it. So AC generator and dynamo. So it's a device which convert mechanical energy into electric energy. AC current. And that electrical energy or that current is basically AC. So it generates AC. The next is principle. So it is based on the principle of electromagnetic induction, on Faraday's law of electromagnetic induction, and this Faraday's law of electromagnetic induction says whenever magnetic flux linked with a coil change, EMF is induced in it. In AC dynamo, this magnetic flux change due to rotation of coil. In AC dynamo, flux change due to rotation of coil in uniform magnetic field. Rotation of coil in uniform magnetic field. The next is construction of this AC dynamo. So AC dynamo consists of magnets. It consists of two magnets, north pole, south pole of the magnet. So these two magnets will generate a magnetic field. So it's north pole of the magnet. This is the south pole of the magnet. So there is a magnetic field here. This is the magnetic field. So in this magnetic field, a coil is placed, a rectangular coil is placed in this magnetic field. So this is the rectangular coil which is placed in the magnetic field. This is basically an armature. This is a frame, and over this frame, this is the frame, and this is the axis of the frame. This is the axis about which this frame will rotate. This is rotating about this axis. So over this frame, you take tons of coil, conducting coils over this armature. So this is basically a frame, and over the frame, the coil is wound. Then here you have two rings basically, and through these rings, two brushes are connected. Basically, the diagram is exactly same that you have done in class 10th. In class 12th, the major stress is not this diagram. The major stress is basically the theory, the calculation, how it generate that induced EMF. So these are the magnets, field magnet. Means magnets will generate magnetic field. These are field magnets. This is the armature. This is the armature. These are the brushes. This is your load. And these are rings basically, slip rings. See what happened due to rotation of this coil. Okay, I'm just straight. Due to rotation of this coil, just a second. No, it's fine. Yes. Due to rotation of this coil about the axis, EMF is induced. Through these slip rings and through these brushes, that EMF flow to the load. This load is basically the device that you are using. If you are trying to light up a bulb using this generator, then the bulb is basically your load. So load is the device which is connected to your dynamo. So this is the construction. So Fatma, is it clear, this construction? Okay. After construction, next is theory. Theory is exactly same that we have did in last lecture. If you remember, we did in the last lecture we studied a coil which is rotating about its diameter. Some EMF was induced in the coil which is E naught sine omega t. That is basically the theory of dynamo. So you can take your n. N is number of turns in the coil. number of turns in coil is in. Then you have A, which is area of each turn. Then you have B, which is strength of magnetic field. Now this coil is rotating with an angular velocity. That angular velocity is omega. Omega is angular velocity of coil. Okay, Fatma, just unmute yourself. Only you are in the class, right? No one else. So can you tell me what parameter will change on rotating the coil due to which flux will change? To change flux, which parameter is changing here? Your flux is BA cos theta. This is the definition of flux. So due to rotation of this coil, which parameter out of BA and theta will change?
Theta.
Can I write theta any in terms of omega? Can I somehow write theta in terms of omega? This we did in last class.
Minus alpha. Theta minus alpha.
What is alpha? Alpha is angular acceleration. There is no relation. Angular velocity. Okay. Fatma, what is linear velocity? Linear velocity is distance by time. In the same way, angular velocity is angular displacement by time. So you can write your theta as omega into t, that second equation. Right? This is how we can convert theta into omega. So if I substitute 2 in 1, I will get that your flux is, it's BA cos omega t. This is your flux. So Fatma, is this flux constant or variable?
Variable.
How would you decide whether this is variable or constant flux?
Because theta is not constant.
There is no theta in this equation. But just by looking at this
omega.
Equation, omega is constant. Just by looking at this equation, how would you decide whether it's constant or variable? Because B is constant, A is constant, omega is constant. Angular velocity is not changing. Angle is changing.
Time.
Yeah, time. The quantities which depends on time are basically variable quantities. So this shows that your flux is changing with time. Now, if your flux is changing with time, I need to calculate induced EMF. I'm going to the next slide. So this is your phi, which is BA cos omega t. So now we have a changing flux. How would you calculate induced EMF using this changing flux? Using Faraday's, so you're not revising anything. Huh? Using Faraday's law. Do you remember what is Faraday's law of electromagnetic induction? Is how would you calculate induced EMF using Faraday's law? It's minus of d phi over dt. So minus of d over dt of phi. Phi is BA cos omega t. Now what is, I'm taking this B and A outside. This is d over dt of cos omega t. So your E is minus of BA. What is derivative of cos omega t?
Sine, minus sine.
Yes, it's minus sine omega t. But see here, it's not just cos, it's omega into t. It's cos omega t. So this constant will come outside. So that's minus of omega sine omega t. So this is your induced EMF, BA omega sine omega t. Just by looking this equation, can you tell me whether this EMF is constant or variable?
Variable.
How are you deciding that this is variable?
So T.
This EMF is variable. And it is varying with this sine function.
Because of T.
Because of T. And along with T, you have a sine function. Fatma, you have maths?
Yes, sir.
So sine is a periodic function, right? It repeats itself after a period of 2 pi. Like sine 0, sine 2 pi, sine 4 pi, sine 6 pi, sine 2 and pi, all are identical. So it repeats itself after a period of 2 pi. So if EMF change according to a periodic function, then this EMF should also be periodic. That this EMF will repeat itself after a fixed period, after a fixed interval of time. So these type of variations are known as sinusoidal variation. In class 11th, you had a chapter by the name of simple harmonic motion. In simple harmonic motion, you must have done these type of things. So this is sinusoidal variation. It's changing with time. Fatma, can you tell me the maximum value of EMF? For what value of sine this EMF is maximum? Because EMF depends upon time through this
1.
function. Yes. So for maximum value of EMF, your sine omega t should be 1. Plus 1 in fact. If your sine omega t is plus 1, you can substitute this value of sine omega t here. It comes out to be BA omega multiplied by 1. So this is the maximum EMF, which is BA omega. So if I substitute it here, it comes out to be its E is E max sine omega t. So this is the EMF that your AC dynamo, the generator, generate. So the EMF that the generator is generating is not constant, it's variable. It's continuously changing with time. So generator does not generate a DC EMF. It does not generate DC current. It generates AC current. It's changing with time. So if I plot the graph, you know the graph of sine function? So this is your graph of EMF. This is the maximum value. The maximum value of this Emax. This is Emax and it's changing with time. Now if I take time, this is 0. This time is capital T. Capital T here is time period. The time period means time taken to complete one revolution. Means the time taken by this coil to complete one revolution. The time taken by this coil to complete one revolution is capital T. That's capital T. This is T by 2, half revolution. This is T by 4, 1/4 revolution. This is 3T by 4, 3/4 revolution. So EMF is maximum at T by 4 and 3T by 4. At 0, T by 2 and T, your EMF is 0. So this is how your EMF varies. And this is what you call AC EMF. And the current which flows due to this EMF, because of current flow due to EMF. And the current which flows due to this AC EMF is basically your AC current. A man pedals a stationary the Emax is NBA omega. That's it. So number of turns are, so this is B omega. If your coil have n number of turns, it's multiplied with n. That's it. So your n is 100. Your B is 0.01. Your area is 0.1. It's half a revolutions per second. Your omega is half revolutions per second. But revolution is not the SI unit. You need SI unit. Convert this in radian. It's 2 pi radian per second. That's the SI unit. Is it one revolution or one rotation means your angle changed by 360 degree. So if it is written revolutions per second, you're supposed to convert this revolution into radian. So just multiply it with 2 pi. So your omega comes out to be pi radian per second. Just multiply all values here. Your n is 100, your b is 0.01, your area is 0.1, your omega is pi. So E max is 0.1 into 3.14. So yours E max is 0.314 volt. So this is the maximum EMF. 0.314 is the maximum. So from now, the circuit starts. So when we were doing DC circuits, the source of current was a DC current, that was a cell or a battery. But from now onward, the source of current is not a cell, rather the source of current is a generator, a dynamo. So the equation of AC EMF, equation of AC EMF is the equation of AC EMF. E is E naught sine omega t. Now you know how this equation derived. This is basically the equation of AC dynamo. Let's look at each and every term. This E naught is the maximum value of EMF. Maximum value, or this is also known as peak value, or this is also known as amplitude of EMF. This is amplitude of your EMF. That's E naught. Similarly, you can level this E. This E is the instantaneous value of EMF. This is instantaneous value of EMF. Similarly, this omega is the angular frequency. This E is E naught sine omega t. Omega is angular frequency of coil. Or this is the frequency which with your AC will change. So this is the equation. Now, when a quantity change, you can do statistics with that quantity. Like you can calculate various types of averages. So in the first part of AC, we will calculate various types of averages related with this EMF. We will calculate average for the whole cycle. Whole cycle means average when the coil complete one rotation. Afroza, how much time this coil takes to complete one rotation? See if I return to this diagram. Then can you tell me the time taken by the coil in this circuit to complete one rotation? So for the full rotation, the coil takes time which is equal to time period capital T. We will calculate average for the time capital T. Then we will calculate average for the half time, T by 2 time. And similarly, then we will calculate one more type of average which is known as RMS value of EMF. After equation of AC EMF, the next thing is you can calculate average value for full cycle. You can calculate average value of AC for full cycle. For the full cycle, the average value of EC you're supposed to calculate. The equation of AC EMF is this. E is E naught sine of omega t. This is the equation of AC EMF. So usually when you calculate average of numbers, you add those numbers and divide by the numbers basically. Number of terms. But here, numbers are not given. You have given a function of EMF. So in this case, to calculate average, we represent average in this way. And the formula for calculating average is this. You will integrate your EMF from some 0 to the final limit, that's t. Then you will divide it by the whole time period. This is basically equivalent. If I give you 3 terms, E1, E2, E3, and let's say one more term, E4. Fatma, how would you calculate the average of these 4 terms? If I'm giving you four separate terms and ask you to calculate the average of these four terms. Yes, Fatma. How do you calculate the average of these?
Add and divide.
You will divide by
Add them and divide by 4.
add them and divide it by 4. So instead of adding, if you have functional form, you will integrate it from 0 to t. Instead of adding, you will integrate it from 0 to t and you will divide it by t. So you can write that average value of EMF is at 0 to t, it's EMF, which is E naught sine omega t dt divided by the time period t. You can do one more thing. You can take this E naught as constant. It's 0 to t, it's sine omega t dt divided by capital. So to calculate average of a function, you don't add them. Instead of adding, you integrate it from the initial to the final limit. Now, if you want to integrate this sine omega t, the integral of sine is it's cos omega t. That's the integral of sine. And see, along with t, you're getting a constant omega. Just divide it by omega. It's 0 to t. Then you have this t in denominator. This t in denominator. I can take this omega outside this integral sign. So the full cycle, this EMF comes out to be its E naught by omega t. It's cos omega t. Limit is 0 to t. So this is the average value of EMF. That E naught by omega t is, instead of t, substitute capital T. It's cos omega t minus cos 0. Next, you can write that omega is angular frequency. You can even write your angular frequency as 2 pi by capital T. Even if you are using this relation, omega is theta by t. If coil completes one rotation, then the angle is 2 pi. Instead of theta, you have 2 pi. And the time taken to complete one rotation is capital T. So here, instead of omega, you can write 2 pi by t. So the average value of EMF comes out to be, it's E naught by 2 pi by t multiplied by t is cos 2 pi by t into t minus cos 0. So t will cancel t, this will cancel this t. Average value of EMF is E naught over 2 pi. It's cos of 2 pi minus cos 0. How much is cos 2 pi? Cos 2 pi is 1, cos 0 is 1. So you can write that average EMF is E naught by 2 pi. It's 1 minus 1. 1 minus 1 comes out to be 0. So the average value of EMF for the whole cycle is 0. This is the average value of AC for full cycle. Okay. After this full cycle, we can also calculate the average value of EMF for the half cycle. The average value of EMF for the half cycle. Okay, Fatma, can you tell me what changes you will made in this derivation to calculate average value for half cycle?
It will not be from 0 to t.
It will be from 0 to what?
T by 2, I guess.
Good, t by 2. Divided by t by 2, right? So limit
Yes.
is t by 2. This is t by 2. Very good. Then you have t by 2. You have t by 2. This is t by 2. This is t by 2. You can take this 2 outside. This is t by 2, right? So along with these terms, you have an extra factor of 2 here. When you substitute these values, this is t by 2. So you have an extra 2 here. So an extra 2 here. So it's t by 2. This 2 will cancel this 2. You will get pi. And there's just small variation in the notation. For average value of half cycle, we don't write this and in this proper sign of modulus. We write this in this way. We write this as EM. Average value for half cycle is represented by EM. So that's EM. That's EM. EM. That's it. So this is EM. This is EM. So this 2 will cancel this 2. Your EM comes out to be its E naught by pi. Your cos pi is -1 cos 0 0. I have left something. Sorry, integral of sine is minus cos. So there is one negative sign here. Padma, please put negative sign in the previous derivation too. It's minus of cos. Although it was 0, but put a negative sign. Put a negative sign here, a negative sign here, a negative sign here. So it comes out to be 2 E naught by pi. So this is the average value or the mean value for the half cycle. So the mean value for the half cycle comes out to be it's 2 E naught divided by pi. 2 by pi E naught, you can write this as it's 0.637 of E naught. This is the mean value of AC for the half cycle, which is 0.637 of E naught. Okay, after this half value for this average value for the half cycle, there is one more definition for the half cycle. So this average value for half cycle. The way we did this derivation is purely mathematical. But as you have noticed that this average value of EMF is a constant value. And that constant value can be say as a DC value. It can be said as a DC value. So you can connect this through this DC value, you can connect AC with DC. Sometimes you can get some conceptual questions over it. Like there's one question which says, I'm basically writing a statement, then I will explain that statement. You can get conceptual questions over the statement. So average value of AC for half cycle is value of DC EMF which will flow same amount of charge through a resistor in time t by 2 as sent by DC through the same circuit just a second, as sent by AC through the same circuit in same time. So basically through this average value, you are comparing AC with DC. So let me explain this thing. So this is a resistor. You have connected this resistor through an AC supply. In time t by 2, some charge Q flows through the circuit. You measure this time, this measure the value of charge. This charge is Q. And you have connected the resistor through this AC supply. So this resistor is connected to the AC supply. In time t by 2, some charge Q flows through the circuit. Then what I do, I take the same resistor, but instead of the AC supply, I connected a DC supply. I call that DC supply as EM, average value or the mean value. And the same time t by 2, I'm asking you to get the same charge. So through the same resistor, in the same time, you need the same charge, but the supply that you are connecting is a DC value. So the DC EMF that will send the same amount of charge through this resistor in time t by 2 as sent by this AC through the same resistor in the same time is your average value. So that average value of AC for half cycle is value of DC EMF. I'm not calling this as AC EMF. Average value is DC EMF because it's constant, which will flow same amount of charge through a resistor in time t by 2 as sent by AC through the same circuit in same time. Same time. So through this average value, you can connect AC with DC. So Fatma, is it clear?
Yes, sir.
Because you can get many conceptual questions on this definition. See, the equation of AC EMF is equation of AC is this: E is equal to 20 sine 340. This is the equation of AC EMF. It's 20 sine 340. Calculate first part. Average value for full cycle. Second part. Average value for half cycle. So Froza, average value of any EMF for full cycle is always zero. Full cycle means I'm calculating average in the time 0 to capital T. It's always zero. This you have missed. This derivation you have missed. And average value for the half cycle is this. This is the relation to E naught by pi. What is E naught? E naught is the peak value. The standard equation of EMF is this. It's E naught sine omega t. So instead of E naught, I'm using 20. So E naught is 20. E naught is 20 volt. So if I substitute 20 here, the average mean value or the average value is 2 into 20 by pi. The mean value comes out to be 40 by pi. The next is RMS value. So before using RMS in AC, let's understand what this RMS actually means. RMS is a type of average. The full form of RMS is root mean square. See how you calculate this type of average. Let's say you have few values of A1, A1, A2, A3, and I ask you to calculate average of this. For average, what you will do? You will add these three quantities and divide it by 3. But if I ask you to calculate the RMS, root mean square, then what you will do this operation in the reverse order. Means first you will square each quantity. For RMS of A, you will first of all, you will square each quantity. Then you will take mean. For mean, just add them up and divide it by n. Then you will take root. This is how we calculate RMS of any quantity. Means if I give you 3 numbers, I give you 1, 2, and 3, and I ask you to calculate the RMS of these numbers. So what you will do, you will first square them, take their mean, and then their root. So RMS comes out to be 9, 1, 10, 14 by 3. But If you don't have, the numbers are not given, if functional form is given, then to calculate average or RMS, you will not add, you will integrate. You will take a square, you will integrate it from 0 to some time, then you will divide it by t, and then you will take integration. So square is a square. Instead of addition, you are integrating it. Instead of dividing by n, you are dividing by the limit t, and then you are taking root. So if functional form is given, which would be given in EMF and current, then you will take RMS in this way. The next is RMS value of AC EMF. So the equation of EMF is this. This is the equation of AC EMF. It's E naught sine omega. RMS can be calculated in this way. ERMS you can calculate as it's E square dt divide, limit is from 0 to t, divided by t, and then its root. This is the formula for RMS. Instead of E, you can substitute this thing. So your ERMS basically comes out to be its root over. This is 0 to t. Instead of E, you can substitute this term. It's E naught square sine square omega t dt divided by t. This is the RMS. This integral is a bit complicated. You can write this as this is root over. You can take this E naught square outside the integral. Sorry. This is 0 to t. This is sine square omega t dt divided by t. This is it. Next, you can take this E square outside this integral sign, and your ERMS comes out to be it's E naught divided by t. Well, this t is inside integral, so I cannot take this outside. Keep it inside integral, inside the root. E naught square by t. 0 to t sine square omega t. To integrate the sine square omega t, you have to convert this in cos. Cos 2 omega t is 1 minus 2 sine square omega. So from here, I can convert this sine square omega t in terms of this cos 2 omega t. Cos 2 omega t, I can write from here, I can write sine square omega t. You can take this thing to the left side, 1 minus cos 2 omega t divided by 2. I can substitute it here. The ERMS comes out to be, it's integral of, it's E naught square by t. It's 0 to t. It's 1 minus cos 2 omega t divided by 2 into dt. Now you can take this 2 outside the integral. I don't have much. Okay, just remember this thing. E naught square by t, 0 to t, 1 minus cos 2 omega t by 2 dt. So ERMS is its root over E naught square by t. It's 0 to t, 1 minus cos 2 omega t by 2 dt. Square by t. Fine. Now you can take this 2 outside. Take this 2 outside. It's a lengthy calculation. You can take this 2 outside, so this comes out to be 2t. It's 0 to t, 1 minus cos 2 omega t dt. Next, what you can do is you can break this integral into two parts. So what you can do is you can break this integral into two parts. You can just write this as it's E naught square over 2t. It's 0 to t dt minus it's 0 to t cos 2 omega t dt. Is it? So your ERMS is it's E naught square by 2t. The integral of dt is straightforward, right? It's t, the limit is 0 to t. And remember, this is a standard integral, it's 0. I have solved this type of integral while calculating the average. Okay, I'm solving it again. You can remember this directly that this is basically 0. I'm integrating again. The integration of cos is sine 2 omega t by 2 omega, limit is 0 to t. So ERMS is it's root over E naught square by 2t, right? It was 2t. Yes. And then you have this is t, limit is 0 to t, minus 1 by 2 omega. It's sine of 2 omega t. It's 0 to t now. So the ERMS is it's root over E naught square by 2t. This is t minus 0 minus 1 by 2 omega. It's a sine 2 omega. You can substitute limit, it's capital T minus sine 0. Next is this is ERMS. This is root over E naught square by 2t. This is t basically minus it's 1 by 2 omega. See, you can substitute instead of omega, you can write this omega as 2 pi by t. So this comes out to be sine 2 into 2 pi by t multiplied by t minus sine 0, which is 0. It cancels with this t. How much is sine 4 pi? Okay, sine 4 pi is 1. Good. Fatma, sine 0, sine 2 pi, sine 4 pi, sine 2n pi. 0. Minus 0. That's why this term comes out to be 0. This is what I was telling that this second term will reduce to 0. If you don't have time in exam, you can directly write this integral as 0. Your marks will not be deducted. So your ERMS is root over E naught squared t by 2t. T will cancel this t. Your ERMS comes out to be its root over E naught square by 2. Next, what you can do is you can write this root over E naught square as E naught divided by root 2. This is ERMS. And this comes out to be 1 by root 2 is 0.707 of E naught. So this is the RMS value of EMF. It's E naught by root 2 or 0.707 of EMF. Solve this question. So before starting this question, there is one more note. Just like the last section, we have connected this thing. Like we connected average value of EMF for the half cycle with charge, right? It was connecting AC and DC through charge. Similarly, using RMS, you can connect DC and AC value, but now instead of charge, you will use current. ERMS is value of DC EMF which would dissipate same amount of heat through a resistor in time t as dissipated by AC through same circuit in same time. This is known as RMS value. So it will dissipate the same amount of heat as dissipated by AC through the same circuit at the same time. So this statement basically says if you have a resistor, you connected this resistor to a source of, this is the symbol of AC supply. This is basically the symbol of dynamo, generator. This is a symbol of cell and this is a symbol of AC supply. And you connected this to an AC supply, E is E naught sine omega t. It's a well-known fact that if you connect a resistor with an AC supply, then some heat will dissipate across that resistor. So in time capital T, some H amount of heat get dissipated across this resistor. Then what we do is we remove this AC supply and instead of AC supply, we connected a cell of EMF ERMS. Resistor is R. And the condition is in the same time you need same heat. So same resistor, same time, you need same heat, but instead of AC supply, now we're connecting a DC supply. And that that particular DC supply is known as ERMS. This is what this statement says. So remember, this RMS, through this RMS value, you relate AC with DC by connect through this heat. So that heat is same. Okay, solve this small question. Equation of AC EMF is E is 10 sine 314t. Calculate first part. Peak value of AC. Second part. Average value for full cycle. Average value for full cycle. Third part. Average value for half cycle. Fourth part. So you need peak value, average value for full cycle, average value for half cycle, angular frequency, fifth one. Then you need RMS value, sixth one. You need EMF at T equal to pi by 6 into 314 seconds. Solve it. Okay. See, in the first part, if I write the standard equation of EMF, that's E naught sine omega t. Okay. So I'm writing it on the next slide. So your E is 10 sine 314 t. So the standard equation is this E naught sine of omega t. So if you compare this with the standard equation, you will get E naught equal to 10. So the peak value means the maximum value, that's 10 volts, just by comparing it. Then you need average value for the full cycle. For the full cycle, average value is always 0. No need to calculate. Third part, you need average value for half cycle, right? For half cycle, this is E naught into 2 by pi. So it's basically 10 into 2 by pi. It's 20 by pi volt. Or if you want, this 2 by pi is 0.637. You can even write this as it's 0.637 of E naught. 2 by pi is basically 0.637. So 0.637 into 10, which is 6.37 volt. That's mean value for the half cycle. Fourth one. After mean value for half cycle, supposed to calculate angular frequency. If I compare these two equations, instead of omega, I'm getting 314. So your angular frequency is 314 radian per second. After angular frequency, the next thing is the RMS value. Here, the RMS value, which is ERMS, is basically E naught by root 2. So E naught is 10 divided by root 2 is volt. So that's ERMS. In the sixth part, is asking you to calculate EMF at a particular time. So the time is pi by 6 into 314 seconds. I just choose this time so that your calculations becomes easier. So this E is 10 sine 314t. In this equation, just put t equal to this value. When you put t equal to this value, that's 10 sine 314 into pi by 6 into 314. 314 will cancel this 314. This E comes out to be 10 sine pi by 6. Sine pi by 6 is 30 degree basically. So that's 10 into half. So E comes out to be 5. Yes, Afroza. Is it clear now? All parts? See, this is the basics of AC. You will use these calculations in almost all circuits of AC. These are the foundations. It's just like Ohm's law in circuit theory. Okay. So the way we have calculated this average value and RMS value for EMF, we can also calculate these values for current. So equation of AC current. Equation of AC current. The equation of AC current is this: I is I naught sine of omega t. So instead of EMF, I just write I. If I calculate average value for full cycle, the same results. Instead of EMF, you will just put current. Average value for full cycle. For full cycle, the average value comes out to be 0. This is the average value for full cycle. Next, you can calculate average value for half cycle. Average value for half cycle. For half cycle, this average value comes out to be its 2I naught by pi. It comes out to be its 2I naught by pi. So it's basically 0.637 of I naught. Next, you can calculate average value for full cycle. You can calculate average value for full cycle. Not for full cycle, sorry, RMS value. And it's better not to represent average value in this way. You can just represent your average value in this way. The next is RMS value. RMS is basically I naught over root 2, or it's 0.707 by I naught. So all relations are same. Instead of EMF, I just substituted current. Next, in your exam, you can also get derivations of these terms. Can you derive these results? It's just same as that of EMF. Instead of E, you will just write I. That's it. Whatever calculations we have done for EMF are valid for current. Instead of E, you will just write I everywhere. After this, you should know two topics. One is phase, another is phasor diagram. If you can remember your class 11 syllabus, you have a chapter SHM. In SHM, you must have done these terms, phase and phasor diagram. I just recalling these terms. Not phasor, not phasor diagram right now, phase and phase difference. So if I write the equation of EMF in this way, that EMF is E naught sine omega t. This omega t that I am using, the argument of sine term, this is known as phase. So basically, how your system will change with time is given by phase. This phase will control the time evolution of the system. That's the phase of the system. This omega t is phase. If I write your equation in this way, that E naught sine omega t plus pi by 2, if I write this equation in this way, then this whole term is phase. Whole term is phase. Okay, if I compare this equation number 1 and equation number 2, Afroza, can you tell me they have same phases or different phases? Pi by 2. So this pi by 2 is basically phase difference. So this is how we define phase and phase difference mathematically. The difference in its phases is known as phase difference. And their physical significance that we will do while we doing circuits. It's just a simple mathematical definition. This argument is known as phase. This is phase. The difference between the two phases is basically phase difference. It's pi by 2 in this case. Now, what this phase physically means, what phase difference will do physically, that we will discuss while solving circuits, not right now. The next is phasor and phasor diagram. See what are phasors and what's phasor diagram. Throughout AC, the quantities that you will encounter mostly are phasor quantities. So phasor means quantities which change sinusoidally with time. Means quantities having sine or cos. See, sine and cos are not two different functions. You both have maths. You know that sine pi by 2 minus theta is cos theta. So sine and cos are the same type of function. They just differ by pi by 2. Say sine 0 is 0 and sine cos pi by 2 is 0. So you can say that sine and cos are same types of function. They just differ by angle of pi by 2. So the next thing is phasor and phasor diagram. The phasor means quantities which change sinusoidally with time are known as phases. So phasors are quantities which change sinusoidally with time. So quantities which change sinusoidally with time are known as phasor. For example, if I write EMF in this way, E naught sine omega t, it's a phasor because you're using sine function. If I write your current as I naught cos omega t plus phi, it's a phasor because I'm using cos here. When I say sinusoidally, that means either sine or cos. Both are sinusoidal variation. That's a phasor. The next thing is phasor diagram. The next thing is phasor diagram. So if you look at this phasor carefully, every phasor have three important parts. One is the peak value, another is the phase, and another is the instantaneous value. So this single diagram will represent all these values. A single diagram will show phase, it will show peak value, it will show the instantaneous value. So phasor diagram, it represents phase, peak value, and RMS value in one diagram. That's phasor diagram. peak value, RMS value in one single diagram. That diagram is known as phasor diagram. See, phasor diagram is not a graph. So I'm not drawing graph here. It's a diagram. So the rules of graph are not applicable here. So I'm not mentioning anything on x and y axis because in graph we mention that you're taking one variable on the x axis, you're taking another variable on the y axis. It's not a graph, it's just a diagram. So phasor diagram, to draw phasor diagram, let's take one example. I'm taking this example. E is E naught sine of omega t. So I will draw an arrow for this diagram. The length of the arrow is equal to E naught. Length of arrow for phasor diagram, you will need an arrow. The length of arrow would be equal to E naught. You will need inclination of that arrow with x-axis. The inclination of that arrow with the x-axis is omega t. Inclination or angle with x-axis is omega t. So I'm taking an arrow. Sorry. This is the arrow. The length of this arrow is equal to E naught. This length will represent E naught. The angle with this x-axis is basically omega t. It represents your phase. So the length of the arrow is representing your peak value. The inclination is representing your phase. And if you can draw a projection over here, drop a normal over the y-axis. This projection will give E. This will give instantaneous value. So it's a single diagram then that tells you all three quantities. It will tell you peak value, it will tell you phase, it will tell you instantaneous value. So see, for phasors, you need a diagram which can represent the phase of the phasor, which can represent the peak value of the phasor, and which can also represent the instantaneous value of the phasor. So to represent peak value, phase, RMS, not RMS, sorry, instantaneous value. Please correct it. Instantaneous value. You will represent phasor diagram. It's a very simple thing. Just draw an arrow anywhere in the first coordinate. Anywhere in the first coordinate. Take the length of arrow equal to the peak value. That's the first thing, length of arrow. Then you will need inclination of that arrow with the x-axis. Make that inclination equal to phase omega t. That's a simple thing. Just take an arrow. The length of the arrow is your choice. The length basically will represent your E naught. The inclination of that arrow with the x-axis will represent your phase omega t. That's it. If you can drop a perpendicular on the y-axis, then this length of the perpendicular will represent the instantaneous value. Other quadrants are for different phases. We will see how to use when you will use the other quadrants. But at least for this example, first quadrant is enough. In the next examples, we will see why you would need other quadrants. Let's take one more example. I'm taking this phasor. I is I naught sine omega t plus pi by 2. Now again, you will take an arrow. The length of the arrow is I naught. This is the length of the arrow, I naught. The inclination of the arrow with the x-axis is omega t. But see, here, your phase is not omega t, it's rather omega t plus pi by 2. Your phase is not omega t, it's omega t plus pi by 2. Now, can you guess where this omega t plus pi by 2 will lie? It will lie in first quadrant or second or third, and where? Where this omega t plus pi by 2 will lie? It will lie in first quadrant or second or third, or which one? Good. Second quadrant. Okay. No, Fatma, Afroza, second. See, you're adding something to pi by 2. This is 0 and this is pi by 2, right? Something added to pi by 2 will lie in second quadrant only. Okay, so you will take an arrow. The length of the arrow is this one, I naught. This is I naught. And this angle is basically omega t plus pi. Now tell me, is it clear? This phasor diagram? Usually, we don't draw phasor diagrams of two quantities on separate axes. We try to draw them on a single axis. Let's draw two phasor diagrams on the same axis. That will give you an idea about the phase difference. Like I'm drawing E naught sine omega t, and I is I naught sine omega t plus pi by 2 on the same diagram. So what you can do is take this as E naught. This is omega t. Then you need I naught. I naught is omega t plus pi by 2. Write this as I naught. This angle is pi by 2. The total is omega t plus pi by 2. If you take projection of E naught on the y-axis, this is instantaneous value of EMF. If you take this projection, that's instantaneous value of current. So if you look at this diagram, it's very clear that I naught and E naught have a phase difference of pi by 2 here. So for majority of cases where we use phasor diagram, we will use phasor diagram to show exactly the phase difference. So this is the phase difference here. See, in these derivations, I will use certain concepts. Phase difference. We represent phase difference by phi. We are representing phase difference by this phi. We can write the expression for average power dissipated is ERMS, IRMS cos phi. We will derive this relation, but at the end of this chapter. But I will use this relation right from the first derivation. Like for tomorrow, I will start with these things. So don't worry about the derivation of these things. This we will drive at the end, but you should remember these relations. Here, this cos phi here is known as power factor. This cos phi is known as power factor. This P average is basically the average power dissipated. This is phase difference phi. Here, the phase difference is pi by 2, right? You can write your phi as pi by 2. So this is it.